Stan Gibilisco here with episode number 3 of Imaginary Numbers, or, if you don't mind my being a little bit of a wise guy, episode number 3I. Before we start with this, I would like to make a little plug for this book, Algebra Know-It-All. I wrote it. You should be able to find it on Amazon.com or on BarnesandNoble.com. You might also find it in your local bookstore, if you can find a local bookstore anymore. Algebra Know-It-All. If you have a local bookstore and they don't stock this book, request it. There are 2 books that follow this. It's a trilogy of rather thick books about mathematics that I tried to write hoping, I kidded my editor a little bit. I said that I wanted to revolutionize mathematics education in America by presenting the subject a little bit more like they learned it in Asia. Well, turns out the Asians seem to like this book better than the Americans do. Maybe I'm just not reading the sales figures correctly, but anyway, that's a little bit of an aside. But on page 349 of Algebra Know-It-All, we begin chapter 21 of the book, and it deals with imaginary and complex numbers. So you might use this little lecture series as a kind of a supplement to that book, and also a way to divert yourself from the seriousness and drudgery of the mathematical study so that you can at least laugh at some goofball on YouTube. That is to say, me. Well, let's get back to the concept of the set of imaginary numbers which we can always denote any imaginary number as a real number times I. Well, I being a single unit constant, this positive square root of -1, we see that between the set of real numbers, commonly denoted like that, that has a 1-to-1 correspondent with the set of imaginary numbers. I guess we can write it like that. For every real number, there is one and only one imaginary number. And for every imaginary number, there is one and only one real number. Now, you probably had occasion to use what they call the real number line, where you have a starting point of 0 and you go off in either direction. Negative usually goes to the left like that. Positive numbers usually go to the right like that. And the line, of course, goes infinitely far in both directions, infinitely meaning forever, without end. And there's some debate about the points on this line and whether they correspond 1-to-1 with the real numbers, but rather than get into that bit of semantics, let's just stick with the idea that we can represent the set of real numbers geometrically as a line like that. Well, we can do the same thing with the set of imaginary numbers. All we have to do is multiply every real number by I on this line. Well, 0i and 0 are the same thing. This 0i is the only imaginary number that is also real, and 0 is the only real number that is also imaginary. Now we have the imaginary number line. Well, let's do a little trick. Let's stand that line on its end and make it go up and down instead of left and right. Negative being down, positive being up, 0 being right in the middle. Then we have I, 2i, 3i, minus I, minus 2i, minus 3i, like that, and 0i in the center, but I haven't labeled that for a reason, which you'll discover very shortly. Anyway, here we go, up and down, and that is just like a real number line, except we've multiplied everything by I and we've stood it on end. Now, let's put a real number line right through, intersecting at 0. So we have 1, 2, 3, minus 1, minus 2, minus 3. We put dots here indicating that these go off forever. We can make this a right angle, a 90-degree angle, make sure that the lines intersect. They're both straight, so they both define a geometric plane, a coordinate plane, which is a variation of the so-called Cartesian plane, which gets its name from the mathematician René Descartes, who presumably was the first one to really define and use this plane. But this is a very special type of Cartesian plane because one axis has real numbers on it, the other axis has imaginary numbers on it. And the fact that 0 equals 0i is reflected by the fact that these two lines intersect at that point. Now, we can define various points on this plane. All of the imaginary numbers lie on this vertical line, and all of the real numbers lie right on that horizontal line. What about the rest of the plane? Say this point. The point that corresponds to the real number 3 and the imaginary number 2i, which we'll represent by an ordered pair like that. The real number value is listed first, then a comma, then the imaginary number value is listed second. That's a point. 3, 2, well, what good is that? What does that have to do with anything? Well, as things turn out, we can add real numbers and imaginary numbers together to get quantities that lie all over this plane. We simply define any real number, such as 3 plus 2i, as the point 3, in this case on the real number axis, 2i on the vertical axis. If we have, say, a plus bi, where a and b are both real numbers, that corresponds to the point a, bi on this plane. So, we now have defined a whole new set of numbers, and these are two-dimensional numbers. Note that all of the real numbers are one-dimensional. They go only along one dimension, one straight line. The imaginary numbers, likewise, are all one-dimensional. But if we want to invent this whole new set of numbers by adding any real number to any imaginary number, we get a two-dimensional set of numbers. Interesting. Well, that's all a fun mind game. What's it good for, you might ask? Well, the pure mathematician would say, I don't care. And one of the best examples of a pure mathematician history's ever provided us with was a guy by that name, and he has written a little book called A Mathematician's Apology, which I highly recommend everybody read. It's a book that extols the artistic value of mathematics, and it doesn't matter what it might be used for. The pure mathematician is not going to be concerned with that at all. Let the weaker, smaller minds, I don't mean to be sarcastic at all, but let the practical people worry about the practical stuff, and let the mathematician, the pure mathematician, worry only about mathematics as an art form. Well, okay, so we have invented a brand new set of numbers that's different from the real or imaginary ones. We need a whole plane to represent these new numbers, which you probably know already if you've taken any second-year algebra or pre-calculus. They call complex numbers. Now, complex doesn't really mean complicated. Complex, really the better word would be composite, but that term has already been taken to refer to numbers, whole numbers that are not prime. So they invented the term complex. They're complex because they are a combination of a real number quantity plus an imaginary number quantity. Of course, special instances exist. All real numbers are complex. They're simply of the form a plus 0i, where a is a real number. All imaginary numbers are complex. They're simply of the form 0 plus bi, where b, again, is a real number. But there's all kinds of complex numbers that are neither pure real nor pure imaginary. So we have shown the complex number plane which is a Cartesian plane that represents all of the complex numbers as points. We can also represent them as something called vectors. A lot of people get really spooked, really scared by vectors for some reason. I have no clue why it scares them. But we'll learn about vectors in the next video in this series. Stan Gibilisco signing off for now.